Hello, class. This is Mr. Hart. And this podcast, we want to continue our discussion of energy by talking about conservation of energy. Last time we talked about how we could store different forms of energy and calculate how much work was done to store that energy. But now we're going to get into how objects move based on those energies. Okay. But before we get into that, we have to talk about a term called kinetic energy. Okay. So last time we talked about potential energy, which is energy stored in some form. We're going to use that energy later to move something. But kinetic energy is the energy of something actually moving. Okay? So the big idea here is that these two are conserved. I can move things from potential energy to kinetic energy, or I can move things from kinetic energy to potential energy. I can store it, or I can use it, and vice versa. Okay? So let's talk about kinetic energy, how we actually calculate it. Okay? So kinetic energy, Ke, is equal to 1/2 times the mass times v, which is the velocity of the object, okay, squared. Okay, so kinetic energy is 1/2 mv squared. Okay, so if you think about what this means, it means that moving objects have some energy associated with them. Okay, so the mass is an important factor to how much energy an object has. A big football player, for example, would have more kinetic energy than a small football player. But it turns out the velocity is a really big component. Okay, so even a short football player that's moving really fast that tackles someone would have more energy than a big fat football player that's moving really slow. Okay, so velocity is a much more important factor here. Okay. So let's practice calculating this a couple of times just because it's kind of an interesting equation. And then we'll show how we can calculate movements based on this energy principle. Okay. So we have a child on a bike that has a mass of 40 kilograms. If the bike is moving at 6 meters per second, how much kinetic energy do the child and the bike have? Okay. Well, we start with our equation. Kinetic energy equals 1/2 mv squared. Okay, 1/2 is just a constant. The mass of the child is 40 kilograms. Okay, times the velocity, which is 6 meters per second. Okay, but that is all squared. Okay, so we times that out. 1/2 times 40 times 6 squared. Don't forget the squared, that's the most common mistake. We get that that is equal to 720 joules. Okay? That's how much energy the child and the bike have when they're moving. Now, just as a sanity check, let's make sure we end up with the correct units for joules. Okay, recall that a joule is a Newton meter. So if you look at this, we have kilograms times meters squared on top over seconds squared. Okay? Now that may not look like a Newton meter, but if I rewrite this as a kilogram meter times a meter, we get kilogram times meter over second squared. Well, that is just a Newton. All of this combined gives us a Newton. So we end up with a Newton meter, which is, of course, a joule. Okay. So it turns out, not surprisingly, that is joules. Okay, so we end up with joules to start and joules to finish, which is good. Okay, let's look at another example. Okay, a 1,000 kilogram car has a velocity of 60 miles per hour. How much kinetic energy does it have? Okay, so be careful here because we got miles per hour. So first of all, let's convert that to meters per second. It always has to be in meters per second. So 60 miles per hour is equal to, if I'm not mistaken, we have 2.24 miles per hour for every 1 meter per second. Okay, so basically just 60 divided by 2.24. And we get that that is equal to 26.8 meters per second. Then from there we can just plug it in. Kinetic energy equals 1/2 mv squared, which is equal to 1/2 times 1,000 times 26.8 squared. Okay, we times that out. And we get that the total energy in the system is 35,9120 joules of energy. Okay, which is quite a lot, as you would expect. Okay, but there we go. So it's relatively straightforward to calculate. Just plug it into the formula based on the values that are given. All right, so why is this useful? Okay, we've talked about energy and we have all these weird mathematical formulas we've been throwing around. What are we going to use them for? Well, it finally makes sense when we talk about the law of conservation of energy. Okay, and it's simply stated like this. Energy cannot be created or destroyed, only transferred between forms. Okay. So, if I have potential energy, okay, I have a certain amount of potential energy. I have a boulder sitting on a cliff. And then I start using that energy. Okay, that energy has to go somewhere. It goes into the motion of the boulder falling. Okay, so here's my cliff. Here's my boulder. Okay, right now all the energy is stored in potential. Okay, but once that boulder falls off the cliff and starts moving down, that potential energy gets stored, that potential energy gets transferred into kinetic energy to get it to move faster and faster and faster. So it slowly uses up its potential energy and turns it into kinetic energy so it can move. Okay, but what about when the rock hits the ground? Well, when the rock hits the ground, that kinetic energy gets transferred to the earth. But the earth is much bigger than the rock, so it doesn't really notice that added energy. Okay, but it turns out all the energy in the universe, okay, everything, okay, can't be created or destroyed. It just gets moved back and forth between potential and kinetic and the different forms that exist. Okay, it's either moving or being stored somewhere or in heat, okay, or something like that. But it's never created, or it's never destroyed, never created. There's a finite amount of energy in the universe that just moves around and flows between different systems. Okay? Let me give you an example of this. Let's say you had this question, okay, which roller coaster will not have enough kinetic energy at the bottom of the first hill to carry the car over to the second hill? Okay. Now, intuitively, hopefully you know that the answer is C. Okay, this car cannot go down the hill and end up back higher than where it started. But you could also think of this as a potential energy problem. Okay, when the car is sitting here, it has a certain amount of potential energy. Okay. Now it will transfer that into kinetic energy once it moves. It will have the most kinetic energy down here at the bottom of that hill. Okay. But overall, it can't get back higher than this point because it can't gain any energy. Right? It can't go higher than it started because that means it would get more energy than it started with. Okay. Which would mean it would just go back and forth and back and forth. Okay. It can't gain energy. It can't lose energy. If it does, it loses the friction, but it doesn't really lose the energy in the universe. It's just transferring it to heat. Okay? But that energy is not going anywhere. It's not disappearing. It's not just coming out of the blue. Okay? It has to be transferred between forms. Okay? A really cool example of this, you may have seen this experiment before, where you put a bowling ball on a string and you hold it right up to your face and you let go and it does a big pendulum swing back and forth, okay? And you just have to sit there and hope that the bowling ball won't hit you in the face on the way back, okay? But you don't have to hope as long as you don't push it because conservation of energy says it can only have as much energy as it started with. So it can't go higher than when you dropped it. So that bowling ball would just go forward and back and stop right where your nose was because it can't gain any energy, okay? I recommend watching this video when you can. It's really kind of cool and fun to watch. Anyways, the point is this, okay? Our mathematical representation's kind of a silly one. It's not really a formula. It's more of an idea, okay? And the idea is this. The energy that we have, okay, we'll use capital E for energy. The energy that we start with, the initial energy, has to be equal for any system to the final energy. Okay? And that's a concept, but we'll see how this can be a very powerful tool for finding values mathematically. Okay? So let's look at this problem. Okay. A book falls off a 5-meter tall shelf. How fast is it going when it hits the ground? Okay. Now we've solved this problem before with kinematics using the kinematic equations and how much time it took to fall and stuff like that. And it can be a little bit of a pain to solve something like this. We can solve this a lot faster with the idea of conservation of energy. Okay, so we know the energy initial has to equal the energy final. Well, in this problem, what energies are those? What type of energy do we start with and what type of energy do we end with? Well, to start with, the book's just sitting on the shelf, so it better just have potential energy. And to end with, it's falling, and right before it hits the ground, it doesn't have any potential energy left. All it's doing is moving. So all it has is kinetic energy. Okay? So that is our energy conservation. Potential energy equals kinetic energy. Okay, I'm going to erase this just to give us more room. But now what we can do is you can say mgh equals 1/2 mv squared. Okay? Potential energy equals kinetic energy. Well, these m's are going to cancel out, which is nice. We don't care about them. We'll solve for the velocity because that's what is of interest. So we'll times by 2 and then square root to get the final velocity. Now hopefully this result looks very similar. This is what we got in kinematics. But see how quickly we can solve for that using energy. Then from there we just plug it in. So square root of 2 times 9.8 meters per second squared times 5 meters. We put that all into our calculator. And we get that the book, if I did this correctly, should be falling at 9.9 meters per second. Okay, so V is equal to 9.9 meters per second. Okay, right before it hits the ground. Okay, and see, all we had to do was just figure out what energies we had in the system, and then we can solve for our solutions to problems like that. Okay, let me show you another powerful example. Okay, a boy throws a baseball into the air. If he throws a baseball with a velocity of 8 meters per second, how high does it go? Now, you could take the time to solve for the time of free fall and use that to solve for the velocity, and we could do all this sorts of stuff in kinematics and it would take a while. But again, using energy, this goes by really quickly. Energy initial equals energy final. In this case, it's the other way around. We start with kinetic energy and we end with potential energy. So we have 1/2 mv squared equals mgh, because the ball is just sitting up there. It's not moving when it gets to the top. So we want to know how high it goes when it stops, right? That's the top of the arc. Again, the m's are going to cancel out, which is super nice. But this time we're not solving for v, we're solving for h. So we'll times the g divide by g on the other side. So we get v squared over 2g. Okay, 1/2 times v squared divided by g is that, equals h. And again, we can just plug in 8 meters per second squared over 2 times 9.8 meters per second squared equals, we plug that into our calculator, 8 squared divided by 2 times 9.8, don't forget parentheses, and we should get that the ball goes 3.265 meters into the sky. And that's it. Okay, so again, for any one of these scenarios, if we know what the energy in the system looks like, we can quickly solve for what the object's height or velocity or stuff like that can be. Or if we know what the energy in the system looks like, we can quickly find other values like the height the object reaches, how fast it's moving, stuff like that. And we'll be able to do this in a lot of other scenarios later on as well. Okay? Let's have you do one more problem just for practice. Okay? So, think about this scenario. what is your velocity at the bottom of this hill of this roller coaster? Okay. Now again, this problem would be unsolvable with kinematics because the roller coaster is, bent. Okay, it's not a straight line. We never really talked about working in 2 dimensions. So how do we solve it in this complex system? Well, it turns out with energy, it doesn't matter what path it takes. Okay, it doesn't matter that this hill is curved. In fact, we could do this after the loop-de-loop and it would still be good to get the same answer. Okay, so all we know is that this hill is 43 meters up. Okay, we know we're starting with potential energy and ending with kinetic energy, and we're solving for the velocity, and we get the same result as we got before. The velocity at this bottom of the hill will be the square root of 2gh. Okay, so we just plug in what we know. It's the square root of 2 times 9.8 meters per second times 43 meters. Okay, and when all that is said and done, we get that the final velocity at the bottom of that hill should be 29 meters per second. Okay, that's a really tall roller coaster and a really fast hill. But point is, okay, regardless of the scenario, if we can describe the energies, we can find the values, which is super helpful. We don't have to worry about straight lines anymore. Okay, we can do all sorts of crazy things if we can think of it in terms of energy. Okay? Cool. So, conservation of energy. We'll talk about this more for sure, but just keep in mind, if you can describe that energy, you can solve for a lot of cool stuff. Okay, so go ahead and do the homework on kinetic energy and conservation of energy. Hopefully that all made sense. Let me know if you have any questions, and thank you for watching.